this. What is like the one thing you could do just to make it that? Yeah. Interchange the first and second row, right? So literally the inverse of this guy is the guy that just does that exact same thing. So E inverse. So if I want to interchange the first row to the second row, you just, so again you can just do this. So you do that 1 0 0 0 0 1. So yeah, it is actually itself, right? The inverse. So yeah. So I mean, from here to here, it's literally just R1 to R2. So clearly, these elementary matrices have its inverse, and it's actually very easy to find, right? It's not that hard. Okay, so now let's talk about how we can express when a matrix A is invertible in terms of these elementary matrices. So now we can state when a matrix is invertible. Why? Because, like I said, the only way to transform this to this is if I interchange the first and second row, which is exactly what this matrix does, right? I mean, if you don't believe me, you can like literally just multiply them together, and you'll get that identity, right? So, yeah. Again, yeah. Okay, so what was I doing? Oh yeah, matrix is invertible in terms of elementary matrices. So theorem 2.4.2. So let's say let A just be some square matrix. A is invertible if and only if it is a product of elementary matrices. Okay? So literally, if you just take elementary matrices E1, E2 to E, all the way to En, and if A can be obtained by multiplying all these together, then A must be invertible. Okay? That's all this is saying. Okay, well, so in the homeworks for the, I guess, week 3 or week 4, I'm not sure which one. A lot of them ask you, well, I don't think all of them, but maybe a few, but they ask you to express a matrix A as a product of elementary matrices. So let's actually investigate how to do this. So the process is illustrated in the following example. Okay, so let's take example 2.2. Sorry. Right. A equals -1, -2, 3, 8 as a product of elementary matrices. Okay. So how do we do this? Well, so basically what you want is you want to Did I do this? Yeah. Okay, so I'm sorry. Yeah, I was just confused about whether or not we've done this already. So the first thing that you want to do is take this matrix and RREF it all the way to hopefully the identity. Now the key part of you being able to write a matrix A as a product of these elementary matrices, it has to reduce down to the identity. If it doesn't, then you can't. And that's and it's reflected on in the theorem. You know, it's invertible only if and only if it can be written as a product of elementary matrices, and you'll see here right now. But yeah, so you literally just do that. So reducing down to say RREF. So you start off. Let's make that first one into just positive one, right? So you get 1, 2, 3, 8. Let's get rid of 3. So row 2 minus 3 row 1. That will give me 1, 2, 0, 2. Okay, now let's get rid of, and now let's make that 2 a 1. So now we have row 2 scaled by 1/2 as 1, 2, 0, 1. And then, since we're looking for RREF, we have to make that 2 a 0 as well, right? So you take row 1, replace it by row 1 minus 2 row 2, which gives you 1, 0, 0, 1, which is the identity now, right? So now all you do is how we did in the last example we did last time. Just label all these operations you did, right? And we will what should we call it? We will write down their elementary matrices. So let's see, I'm going to put it here. All right, so yeah, you can see it. So the first matrix. So all we did was scale the matrix, the first row by 1, right? By -1, sorry. So we leave that alone, and we scale the first row by -1. 2. So we took the second row and subtracted it. So we only replaced the second row. So the first row is still fine. So that one you leave alone. And then the second row you will have to. So you take -3 and 1. So you multiply the first row by -3 and then added it to row 1, row 2. Sorry. Okay, so now let's take a look at 3. So you scaled the second row by 1/2. So leave the first row alone, and you do 1/2 down there. And then 4, you took the first row, scaled the second by 2, and then you left that one alone. So now these are going to be my E1, E2, E3, and E4, right? So now let's look at how we can write this as a product. So let's resize it a little. Let me just put it right here. Okay. So now look. Take A, right? Whatever A was, multiply by E1, E2, E3, and E4, right? And what did this give me, by the way? Once I did all this, what matrix did this product give me? Yeah, the identity, perfect. And now let's use the theorem that I stated saying that the inverse for elementary matrices exists, right? So now multiply both sides by the inverse of this guy, right? So literally just multiply both sides of this. By come on. So resize this. So just take E4, E3, E2, E1 inverse, right? And also when you do like matrix equations, the side you multiply the matrix on, you have to also multiply. So since I multiplied on the left side, you have to multiply on the left side. Come on, make it smaller. E4, E3, E2, E1 inverse. These two cancel out, and you're left with A is equal to, well, anything times the identity is just the identity, it's just that matrix. So you're just gonna get E4, E3, E2, and E1 inverse, right? But remember the one of the results I gave you, if you take the inverse of A times B, it's just equal to the inverse of B times the inverse of A. Remember that one? This one. Remember that one? So we can apply it to this guy. So that means A is just going to equal to E1 inverse. Oh, sorry. Did I? Yeah, that's right. What did I? Switch it over. Yeah, that should be right. Yeah. E2 inverse. Yeah, that should, yeah, perfect. Okay, so now each one of these is an elementary matrix, and their product is also elementary matrix as a result as well. So this is literally how you get this. Now, key point. Remember that theorem I said a matrix is invertible if and only if it's a product of elementary matrices? Why did this work? The only reason it worked is because this reduced down to the identity, right? If it didn't reduce down to the identity and we multiply both sides by this giant matrix, it would no longer just be a product of elementary matrices, right? It would be a product of elementary matrices and then another matrix that might not be elementary. So that's why that theorem is true. Okay, so let us state what happened to the I. The I is the identity. So any matrix times the identity is the matrix itself. It's like 1, like for real numbers, right? Any number times 1 is equal to that number. You don't ever write 1, right? So in matrix land, the identity acts like the number 1 for real numbers. So yeah, so this is just the process of doing this. So let's state one last important theorem, and then we'll move on to LU factorizations. So 2.4.3. So now let A be a square matrix. The following are, I guess, the following statements are equivalent. Okay, so what are these statements? Well, A is invertible. 2, the matrix equation AX equals B has a unique solution for every vector B. 3, AX is, so the homogeneous equation AX equals 0 has only the trivial solution. So trivial solution just means means x equals 0. So x equals the 0 vector is the only solution. Okay. 4, A is row equivalent to I, and then 5, A can be written as a product of elementary matrices. Okay, so I just want to talk about really quick what this all means. So what I mean by these statements are equivalent means if you have one, all the others must be true. So if A is invertible, then all the other ones are also true. If AX equals B has a unique solution, then A has to be invertible. It's row equivalent to I, and so on and so forth. So that's how you interpret this statement, right? So as long as you have one of these being true, all the others are true now, okay? And thinking of them in these different ways, it will help a lot later on. All right, so let us now move on to LU factorizations, okay? So you've heard the word factorization in college algebra, you know, factoring a polynomial, right? You take a quadratic and you factor it as a product of two linear terms, right? You like break it apart, right? Same thing for this guy. And LU factorization just means you factor the matrix and you break it apart into two different things. You can break it apart into many more, like it doesn't just have to be two different matrices, it can be many. And we'll see why that's important here in a second, because I mean, why do this? So first, let's define it. So first, let's define triangular matrices, okay? A matrix, say B, is said to be triangular, or I guess you could say upper or lower triangular if all, I guess let's just put the form, if it has the form, so B equals, so for upper, I mean you can have like I don't know, like A1 all the way to AN, and then you have just a bunch of stuff up here. They can be numbers, zeros or whatever, and then but the requirement is that it has to be 0 below this, okay? So you see how it like forms like a triangle, right? So upper triangular means you have stuff in the top and then zeros down and below, okay? And then same idea for lower triangular, right? So if it's lower triangular, it just means that you have stuff here and then zeros up here, okay? So again, and then you have let's see, a lower triangle down there. So upper, lower. Okay, that's all that means. So now let's define LU factorization. A matrix, say A, and let's say it's square. It doesn't have to be square, but we'll just do it for this class. If is said to have a LU factorization if it can be written as a product of a lower triangular matrix L and a upper triangular matrix. Say U, right? So now you know why it's called LU. L for lower, U for upper. So let me. So then you write it A equals L times U, okay? So like I said, you broke the matrix A into the product of two other matrices, okay? L and U. Okay, so now you could ask, like, why in the world why would we even want to do this, right? There's absolutely zero reason to want to do this. Well, this is where more application stuff comes in. So I guess for example, really quick, let's say A is equal to 1, 2, 1, 0, then a LU factorization is, you can break 1, 2, 0, 1, 0 up into 1, 0, 1, 0, or 1, 1, sorry, times 1, 2, 0, minus 2. So you see how this one's lower triangular, the other one's upper. So this one is the L and this is the U. So now let's pose this question. Why go to all the trouble of writing our matrix like this, right? It's like, well, I mean, why in the world would you ever want to do this? Well, the answer is actually motivated by basically industry problems, business problems, and even computer stuff, right? And all of it had the problem of computation time. So computation time on large problems are reduced significantly. All right. I'm not sure. Oh yeah, so don't worry. I'll tell you. I won't just like say this is L and U, and I'll tell like right after I cover why we need LU, I'll actually give you an LU algorithm. It's like super easy. Like all you gotta do is like use RREF and just keep track of everything and just fill in your matrix. That'll be after this. But right now I'm just telling you why, like in the world, why do we even need this in the first place? So I don't know if you guys know, but like while it's true that your computers can do operations like a million times faster than you, they're not like they don't have like infinite speed either, right? You have there are sometimes you have I mean you run into the problems of complexity, right? You have time complexity, space complexity. If your algorithm is like, I don't know, like big O of e to the n, and you'll have to wait until the end of time until that thing is finished. Um, so in industry, in business, we had the problem, right? We have the problem where they had like a bunch of systems of linear equations that could be like hundreds of equations and hundreds of variables, and then your matrix can be 100 by 100, right? And then your computer has to do the RREF kind of thing on it. So if it gets like super big, like a million by a million type matrix, your computer's not gonna like it's not gonna like that, right? So what we do is then we try to cleverly avoid it, and one of the things is this LU factorization. So it's so it is fairly common. It is a fairly common industry and business problem to solve, let's say, a sequence. Like, so this may be one problem to solve a sequence of matrix equations, say like ax equals b1, and let's say like ax equals bn, right? So you have a different bn and a different b for your matrix equation. So as it stands now of what we learned, the only two ways that we can solve this is either do RREF in every single one of these, or compute A inverse one time, and then we can like just multiply it to each b. But what happens if you don't have the A inverse, or if you don't want to do all this like RREFs? Well, then you can use literally what we're going to do right now. So if, like say, A inverse existed, then all we need to do is to find solution. It's literally just, I mean, the solution to this would just be A inverse times Bn, right, for every n. Or perform R, R, E, F, n times, right? And then all that has its own like complexity. So again, so before we talk about how to find L and U, let us see how they are used. Okay. So okay. So let's just consider the scenario. Okay. So if A can be written as LU, right? Then the matrix equation AX equals B can be written as, well, LU times X equals B, right? You just replace A with what I just said. And since matrices commute, we can also rewrite it as L times U times X equals B, right? Let's call this guy right here the vector Y. So this L times, U times X will give you a vector, right? So let's call this one Y. So then we get the following matrix equations. So you get these two. You get U times X is equal to Y, and that comes from here, right? And then you get L times Y is equal to B, right? So that is just literally this part times that part, right? Equals B. Okay, so we broke it up. So let's just see it as a mapping. So also when we talk about, we're going to talk about mappings later on. This is good practice for you guys to see this as mappings. So let's just say here's like the space X lives in, right here. Okay, so, and let's just say this is the space where Y lives in, okay? And this is the space where B lives in. So how do I get from here directly to here? Well, I'm just going to multiply A times X, right? A times X will take that vector Bx and give it B, right? Well, I can do the same thing by going over here first by doing U times X, right? That'll give me Y. And then I can do L times Y. So you see how this still gives me the same solution? It still takes me the same place. One takes me directly there, and the other just takes me to a little, like on a little detour, right? So this, you can see that the solution is still the same. Okay. So, remark. Notice that since U and L are triangular, it makes it easy to solve 1 and 2, right? Because remember, when we were solving just normal matrix systems, we always took it to REF, right? Because if it took it to REF, at the very least, we can just take that last variable, substitute it into the previous equation, and substitute that. It's a backward substitution, right? So L and U, having it in LU form already, you already kind of have it in REF form, right? Which makes the computation time much faster already. Using backwards or forward substitution. So now let's see an example on why, or let's see an example of how this is solved. So suppose that A is equal to, say, 3, -3, 6, -9, 7, 5, -4, 5, -2, 1, 0, -5, 2, 0, -5, and 12. And suppose its LU factorization was this. So 1, -1, 2, -3, 1, -5, 8, 1, 1, 3, and then 1. And then everything else here is 0. Okay. So we take it off. Come on. 3, -7, 2, -2, -1, -1, 2, 2, 1, and -1. 0, 0, 0, 0, 0, 0. Okay. So use LU to solve it. To solve AX equals B, where B is equal to, say, -9, 5, 7, 11. Okay. Okay. So so we're gonna run through this. It's not that hard. It's just so solution. So what you do is you can do one of two things. Use that substitution stuff I was talking about, or just adjoin each one, right? So adjoin L with B, and U with Y, and RREF both of them, right? So RREF and RREF. And if you RREF this with the adjoined matrix, you get 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, and then you get 3, 4, -6, -y, and then this one will give you 1, 0, 0, 0, 3, man, I think I copied it wrong, but whatever. So and let's just pretend it gave me, I don't know. So I think I copied it wrong, but so these two are supposed to be this. So basically, so LU, so see, so LU being the X, so it'll be U, it should be U, Y, so let's see, sorry, hold on, I think I messed up, hold on. So you take LB, which will give me, let's see, is this right? Hold on, let me just, give me a second. Yeah, okay, yeah, that's right, that's right. So you join it this way. And then this part I copied down wrong, but I'm not gonna pretend I'm gonna be able to like do it really quick. But let's just say this was A, B, C, and D, right? So solving each one of these is gonna give you the solution. So you just say this is my solution X, this is my solution, that case, say Y. But I mean, but what? Okay, so what? You're not gonna be doing this per se, but what I want to tell you is that this process right here took 12 flops, meaning operations, just the number, like all those. If you count each operation that we do, one by one, that's what flops mean. and then this one took 16 flops. Okay, so what's the whole point of this? So let's see. So if you were to find x this way, if you add 12 and 16, that gives me 28, right? Operations that we did. If you were to do just the normal A, if you were just take A, this one, how it is, and then adjoin it with B and do the RREF, that would take you about like 62 flops, which is double, almost double already, right? So you see that this one took much less time than just doing the RREF on A. So that's the whole point. So finding X using LU takes, so 12, so flops just means, in this context, just means every operation you did. So every row operation you did, you count it one by one. If you do it by hand, you would do 12 on the top, and then you do 16 on the bottom. That's how you calculate flops in this case. Again, so takes 28 flops, and doing RREF on, say, A and B takes 62 flops. And how do I know? How do I know exactly? Because I used the computer to count them off. This is literally the only reason why. Okay, so now that you know that what the advantage is of this, I'll ask the question: how do we find L and U, right? And the answer is we use, well, in its foundation, we use elementary matrices and REF. Okay, so suppose A is reduced to REF, but I have to pose a now condition. I can only use adding multiple rows to each other. I can't use any of the other two, so I'm only allowed that one. Okay, only using adding multiple of rows to one another. Yeah, so one another. And so since we have this, then there exists a sequence of elementary matrices, say A to the K, such that so EK all the way to E1 times A is equal to some matrix U. So if you do the REF, remember that immediately gives you an upper triangular, right? Because you get rid of everything that's below the diagonal. So that gives you the U already. So this is my upper. So first thing you do is try to get it with REF, only using multiple rows of one of each other, okay? And then from here, you can see that if you take the inverse of this matrix, EK all the way to E1, all these will be lower triangular, and the product of lower triangular is lower triangular. So that inverse of this guy right here will actually be your L, okay? So for the last 2 minutes, let me just do an example, because I'm running out of time here. So, and I'll lay it out. And next time I'll lay it out a little bit better. I only have 2 minutes, so. find LU of, say, A equals 1, 4, minus 3, negative 2, 8, 5, 3, 4, and 7, okay? So solution is this. Make two columns, obtain, so you're going to obtain U here, okay? And then you're going to obtain, and you're going to build L here, okay? So your L, just always start off with 1, whatever your size of your matrix is. 1, 0, 1. And then you're going to build the lower part here. So start off with 1, 4, minus 3, minus 2, 8, 5, 3, and 4, and 7. And so since I'm going to be running out of time here, I'm just going to give you the first way, and you're going to repeat this. So again, try to reduce this down to REF, okay? Only using multiple rows with one each other. So I'm going to get rid of that negative 2 by doing 2R1 plus row 2. So if I do that, I get 1, 0, 3, 4, 16, 4, minus 3, minus 1, 7. And then, so here's the idea, and you keep repeating this, and I'll do it next time as well. Look at what operation we did here for row 1, right? Take that number, switch the sign, and then put that right here. So we got rid of this guy. So and so just whatever this guy was, put it here and use the opposite sign. So the next one you're going to get rid of is 3. Whatever you used to get rid of 3, you're going to put right here. So in that case, it would have been 3, and then switch the row, and then in this case, it would have been 1/2. So I'll do it again indeed, yeah. Sorry? Row 2. Oh, yeah, sorry, yeah. So it should be row 2 replaced by that, yeah, you're right. But yeah, either way, this is how you do it. Okay, so I'm already over, so I'll continue this next time, and this will finish the chapter, and we'll go on to determinants next time. Okay. Okay, so.